Okay, thanks Luke a lot for the introduction, and thanks everyone for joining me. Today I'll talk about something in the middle of signal processing, data analytics, and neuroscience. So we live in an era of networks. At the global level, there's a network of transportation, which transports goods and food to sustain our everyday life. At the country level, there's a network of energy transmission, which transmits energy produced by energy producer to energy consumer. At the city level, there's the network of highways, which connect cities to other cities. And at the individual level, we have the networks of friends, family, co-workers. But probably the most complicated networks both you and me have been engaging with is the network inside our head, our brain, which defines who we are and what we do. As a network scientist, we consider networks consisted of nodes and edges. Nodes represent entities have same kind of features and functionality, and edges denotes the interaction between the nodes. Some of you may be confused why a brain is a network, because brain is just a piece of tissue, of volume. Well, if you look at the surface of the brain, there are lots of hues and valleys. Inside the hues and valleys, there are lots of brain regions consisted of nodes have the same functionalities, features, and very different from neurons in other brain regions. Therefore, the nodes in the network can be considered as the brain regions. For each of the nodes, we can use imaging technique such as functional MRI, which measures the amount of oxygen in each of the brain regions. And this can be considered as how active our brain region is. Well, if the brain region is the nodes, what would be the network? What would be the edges? We can use another imaging technique called diffusion imaging, which traces the bouncing of water molecules inside our brain. This bouncing of water molecules can be considered as highways where information is passed, and therefore as an interaction between the nodes. The signals and networks have been studied separately a lot in the past decade. So the question I'm very curious about is, can we define something which associates signals with networks? And maybe this will tell us a lot about the individual differences among human beings. Well, they sound very interesting, but it's not very straightforward, because different subjects may have different networks, and we need a unified tool to accept these differences. Can we do that? The answer is yes, but from a very different field, music. I'm sure many of you sitting here are very good at playing pianos. If you press the left part of a piano keyboard, you're going to hear a low-pitched sound like this, right? And if you press the right part of a piano keyboard, you're going to hear a high-pitched sound like this. Again, low pitch, high pitch. The differences in the sound is because sounds are waveforms. And if we visualize the waveforms, the low-pitched sound is going to be a smooth variation over the time interval it is played. The high-pitched sound is going to be a sound that is very rapidly varying over the time interval it is played. And this difference in the smoothness and variation is why our ear can distinguish these two sounds. Okay, this provides us a way to generalize to more complicated stuff. And instead of considering the underlying structure as the time interval, how about we consider them as the network, as the brain network? And we keep the interpretation of smoothness and variation. This provides us a way to define the low-pitched brain signal and high-pitched brain signal, which we call them alignment and liberality. As an example, imagine our brain just have 6 nodes. They form like 2 different communities, one at upper left, one at lower left, the other at upper right. Nodes in the communities, there are lots of connections. And there are very rare connections for nodes within different communities. The low-pitched signal, the alignment part, is going to be a smooth signal on this brain network. And therefore, for nodes in the same community, they tend to have very similar signals. The high-pitched brain signal is going to be a very rapid one, very rapidly changing one. And therefore, for nodes in the same community, they still can have very different signals. This definition enables us to consider the alignment, liberality, the brain spectrum, even if subjects have different brain networks. And the question we want to ask is, can we use this notion of brain spectrum to find the differences in human beings? To do that, we consider different types of experiments. The first experiment is motivated from playing a guitar, to teach a subject to how to play a guitar. So each subject is facing a screen that have 5 boxes, and the subject needs to respond to the stimulus by pressing the corresponding button using his right finger. So imagine number 3 is highlighted, then the subject needs to press the number 3 button using his middle finger. It's like a game, like a Guitar Hero. And of course, all the subjects at the start of the training, they have no experience with music. They haven't played guitar before. And as they play with this kind of sequence melody, they become more and more familiar with this kind of task. And the first question we want to ask is whether there are some changes in the brain spectrum caused by these differences in the familiarity of the task. The answer is yes. We found at the start of learning, when subjects are very unfamiliar with the task, then the signal is not very aligned on the network. There are lots of variation of the brain signal on top of the network. When the subject becomes more and more familiar with the task, the signal gets more and more aligned. And these are the differences in the brain spectrum. The second question we want to ask is, different subjects, they have different behavior when trying to learn a new task. Some subjects, they can learn how to play a guitar within 2 hours. And some other subjects, they cannot learn that fast. They need a foundation period, maybe 8 hours or 2 days. They learn the foundation of playing guitar, and then they suddenly realize how to play a guitar. And they learn it very fast after 2 hours. So the question is, can we distinguish this thing? The answer is also yes. What we found is, at the start of learning, when everyone is unfamiliar with music, it is good to have alignment signal. If your signal is aligned with the network, it's very smooth, then you are going to learn very fast at the starting of the process. At the end of the process, when everyone becomes very familiar with the task, it is the opposite. It is the liberality, which is the deviation of the signal from the network, makes you further improve your skill. To combine the story, what we find here is, once you're unfamiliar with the task, it is better to have alignment signal, to have a signal that is smooth on top of your brain network. This can be considered as the big picture. You try to learn the big picture first. And once you have the big picture, as you become more and more familiar with the task, this kind of big picture gets accumulated. And once you become super familiar with the task, it is the liberality, the brain signal deviates from the brain networks that makes you further improve your skill. The second experiment we consider is switching attention. Some of us are very good at switching attention. We can talk to our grandmother in 30 seconds, and then start to write an email. Well, some of us are not very good at this. So we designed this experiment to find the differences. The experiment is designed such that there are different types of images. So the green one here is a triangle consisting of squares. Maybe it's too small for you to see. And the white one is a circle consisted of crosses. When the subject faces a green image, they are asked to respond to the big picture, which would be triangle in this case. And when the subject faces a white image, they are asked to respond to the smaller pieces, which would be crosses in this case. We designed 2 different types of sequences. The first type of sequence is always the green image, so the subject always responds to the big picture. They don't need to switch their attention. And the second type of sequence, they need to switch their attention between the big picture, smaller details, and big picture. We want to ask whether these differences in some people are good at switching their attention, some are not, can be analyzed using the brain spectrum. The answer is also yes, and we found is if your signal is very liberal, your signal deviates from the brain network, then you are going to perform way slower in switching your attention compared to the subject, their signal is aligned. So recalling the previous experiment, what we found is when you are unfamiliar with the task, it is the liberality that makes you a slow learner. And what we found here is liberality, the signal deviates from the networks, makes you slower at switching your attention. A kind of unified theory we find here. I think some of you may find, okay, this is interesting, but how can this be useful to the society? Because what we have been doing is like taking measurement using functional MRI different locations of the brain. This is not that different from taking measurements on a chipboard by using current or voltage measure. And it has been shown that no matter how many measurements you take, the current or voltage, there's no way for you to infer the actual chip structure. This is a sad fact because brain, of course, is way more complicated than a chipboard. But what the theory have been developing, what things we have been developing can be used in many areas. And here I'm showing you 3 examples. The first is rehabilitation. For example, patients suffered from strokes. They need to perform rehabilitation session to try to regrasp the skill they used to be good at. And using this kind of scanning, we can try to find the proper time or the optimal time, such that the subject are good at relearning their skills. And now is a good time for them to do the retraining. This has been used as a research in some of the rehabilitation centers. Second, hiring process. Because I've told you that we have found liberality, signal liberality is really positively related with whether you are going to be a slow performer, whether you are going to be slower at switching your attention. This tells a lot about the way you perform a task. Maybe 5 years later, this kind of brain spectrum will be very important to find an ideal candidate for a job based on the brain spectrum. Maybe after 10 years, the first thing HR asks a job candidate, not why do you want to join our company, but let's go to do a functional MRI scan. And based on the scan, they're going to tell you whether you are going to be good or bad at this position. Finally, let's think even further in decision making. All of us make important decisions. Sometimes we made good ones that we felt very thankful about the time we made a decision. And sometimes we are a little bit regretful about the time we made a decision. If this kind of analysis keeps going, maybe we would find the kind of brain spectrum that is very related with the good or bad decision you are making. And therefore, maybe in 20 or 30 years, before you make an important decision, you want to go to a functional MRI scanner. You want to perform a scan, and based on the result, you see, my brain signal is very aligned. Now is a good time for me to make an important decision. With this, I would like to conclude, and thanks very much for your attention.
Questions for Weiyu?
So what kind of errors occur in the fMRI measurements so that you have some kind of error in your data?
Yeah, that's a very good question. I removed the figure, the brain figure from this because I think it's kind of too technical. And this really depends on the task, right? Like in this task, because it requires visual and motor, like you need to interpret from the kind of image, whether it's a big picture, whether it's a triangle or not, and you need to respond to this kind of stimulus by pressing a button. So what we found is the region that are activated in the liberality part is kind of the region that corresponds to the visual and motor regions. And of course, there are smaller differences in that, and we can talk more offline, like the details of this. Yeah, but it depends on the actual task. In this case, it's going to be like visual and motor. In this case, visual is going to be more important after the subject becomes familiar with the task. Like initially, visual and motor, they are both important. But after the subject becomes more familiar, actually you can imagine after they see the first few sequences, they know what's going on at the end because they have become familiar with the task, and it's the visual region that is highlighted. That's a good point.
I just wonder, for example, if I'm a slow learner and I want to become a fast learner, is there any way that I can train my brain from a certain pattern to another pattern?
Yeah, that's another good point. So another application which has been developed in research center is like some patients, for example, Alzheimer's diseases. And then we can use the region that is found to be correlated with the behavior to find these regions and apply some electronic stimulus on these regions. And then there's research that this really helps the subjects to recover from the disease. So I think different way to think about that is we can find the brain regions that are related with better performance. And if you are there enough, you can go to a electronic shock center, which shock the areas that are positively related with a better learner. And this may increase the switch attention ability we have. That's a good point.
So you've been talking about learning. Is anyone studying forgetting?
So for learning and for forgetting?
Yeah.
Yeah.
Like if you're a fast learner, are you also a fast forgetter?
Yes, so that's another very important point. So what we find here is this kind of thing, right? Because we consider alignment and liberality. What we found is the kind of finding we have is kind of similar to existing literature where people talking about they consider children, adults, and then the elderly, right? And they try to use this kind of, not this idea, but similar kind of idea, on the signals to try to find the signal differences between the children and adults, between the adults and the elderly. And they found it's like a triangle, that from children to adults, you kind of change in one direction, and from adults to the elderly, you go back to children, which is like this kind of thing can be correlated as the ability you can do task. We didn't have that kind of data set, like the differences between children and adults, but I think that's a very good area to look at and to see whether this alignment and liberality can exist. My thinking, if you ask me to guess, I think there must be something, like your signal is going to be more aligned or more liberal with respect to a network.
Any other questions? Let's thank Weiyu.